This session is going to be educative about gauge R&R study. Measurement system analysis specifically for continuous data. We call it gauge R&R study, gauge repeatability and reproducibility. And it's a part of MSA, right? So bias, linearity, stability already taught to you. And now the point is repeatability and reproducibility. And together it is called gauge R&R, right? So it's a measure of the precision error. That is what we are trying to measure. Any moment, any time, in any project you collect the data, your data will have variation. Variation can be due to the process itself. This is what is your problem. This is what you are going to control. But in addition to the process variation, which is the real problem, sometimes the measurement system will also bring about some variation. So that should be controlled properly. Then only you will be able to get a clear picture of the process variation, right? So Six Sigma is aiming to reduce the process variation. You can do this very well if the measurement variation is controlled within the prescribed levels. Otherwise, what will happen? You might think that there is a lot of problem, but in reality, there may not be a problem at all. People are simply reporting problems because of the errors in measurement, but in reality, there are no problems, right? So that shouldn't be the case. So doing a project, Six Sigma project is like driving a car. What is important while driving a car? You must clearly see the road and then drive the car. Similarly, what is important while solving a problem? You must clearly see the problem and then solve the problem. Only to ensure that how clear you are in terms of seeing the problem. It depends on the quality of data, right? Quality of data again depends on the quality of the system. So that is why we are trying to assess the measurement system's ability to provide the quality data. All right. So you can see the process conditions better if your measurement system is better. But how do you know whether your measurement system is better or not? First of all, measurement system means the equipment, the operator, the characteristics that is getting measured, the item that is getting measured, the environmental condition, the instructions that are given to them, all of them are part of the measurement system. Anything can go wrong. If any one of the element goes wrong, then the whole measurement system will fail to provide quality data. Yes. So variation can be two types: process variation, measurement variation. Our aim is to control the process variation. Before that, we must be sure that measurement variations are minimal. An industry standard is 10%. And measurement variation, nothing but measurement error, can be broadly categorized into two. One is accuracy error, on the other side is precision error. Accuracy error, you already discussed. Bias, right? The deviation from the true value is called a bias. If the bias is 0, then your readings are perfectly accurate. And then linear stability. Bias over range of reading is linearity. Bias over time is stability. On the other side, the precision can be of two types. One is repeatability error, other one is reproducibility error. Certain books call repeatability error as equipment variation, call reproducibility error as operator variation. But just because it is called as equipment variation, just because it is called as operator variation, it doesn't mean the equipment and operator are responsible for the error. No. Anything, any element of the measurement system can be a reason for the repeatability, can be a reason for the reproducibility. So what is repeatability? Right? If you ask me to measure an item multiple times, let me say you want me to measure 100 mm 10 times. You have given me the standard piece of 100 mm. And all 10 times, when I give you same reading, then my readings are repeatable. Right? I measured the same item repeatedly multiple times, and repeatedly I am giving you the same reading. Then I am repeatable. Similarly, suppose same item, after I measure, now you are measuring. If my readings and your readings are not matching, that means we disagree each other. But both of us are measured the same item. I also measured 100, you also measured 100. Ultimately, we both should come out with the same number. But if that is not happening, that disagreement is called reproducibility error. If we agree perfectly, then we are perfectly reproducible, right? So reproducibility is good, but reproducibility error is bad. You need to understand how to spell out. So this was already discussed in the morning, accuracy and the bias. Sorry, I'm not going to repeat. Right. So these terminologies we already discussed. And resolution. What is resolution? The minimum signal to which your measuring equipment can respond, or the minimum output that can come out of your measuring equipment, or the difference between the two consecutive readings of your measuring equipment. These are all nothing but resolution. In simple language, nothing but the least count. All of you know least count, right? A vernier will have a least count of 0.01 and sometimes it is 0.001. That means, you know, the more, the better the resolution, the deeper will be the information, right? And that is called resolution. And repeatability, the variation in the measurements within the same appraiser. You are employing just one appraiser and asking him to measure just one part multiple times. Same part, same equipment, same operator, but the multiple readings differ from each other. Now, what is this error? This is called repeatability error, right? On the other hand, the variation between the appraiser, that is called reproducibility error. We are going to pinpointedly understand each and everything and measure the repeatability error, measure the reproducibility error by doing a live case study, right? I'm going to make all of you involved in the measurement, and I'm going to make all of you use a measuring equipment, and I will prove all of you are making error, right? And then I will help you estimate the error, right? We'll see that. So bias already discussed. I'm just skipping this. Linearity. And if you look at the blue color line, it's perfectly linear, but look at the green color line, it's not linear. Why it is not linear? Bias keeps on increasing. And see, looking at the control chart, this particular first control chart, all the points are well inside the control limit, whereas the second one, certain points are not touching the control limit and going beyond the control limit and indicating that your equipment is unstable, right? All right, so recommendation is readings have to be stable, recommendation is readings have to be linear, and recommendation is bias should be 0, right? So that your readings are 100% accurate. And now, resolution, I told you, the minimum reading. And now at this point of time, I want all of you to open the stopwatch that is there in your mobile phone. All of you have a mobile phone and all of you have the stopwatch, isn't it? Please open the stopwatch and tell me what is the least count of the stopwatch, or tell me what is the resolution of the stopwatch. All of you can now participate, and preferably you can keep your video on for further discussion to make it lively. Just open the stopwatch.
0.01, sir.
0.01. Very good. Fantastic. 0.01. Can you also tell me the physical, the actual unit of the 0.01? Is it 0.01? Is it minutes?
0.01 seconds.
Very good. Beautiful. This is 0.01 second. That means 1/100th of a second. To that extent, your stopwatch is capable. To that extent, your stopwatch is capable, right? And that means between 1 second and 2 seconds, how many readings are possible? 100 readings are possible, right? So such a really good measurement system all of us have. That 1/100th of a second is called what? Centisecond, right? Centisecond, or you can call it 0.01 second. And now, so resolution is this, the meaning of this. As I already explained, in the definition. Let us say an equipment gives a reading of like this, 2.1, and second reading is 2.2. That means what is the resolution of the equipment in the first row? It's 0.1. When you consider the second row, the first reading is, let us say, 2.01. The immediate next reading is 2.02. Now the least count is how much? 0.01. Something similar to your stopwatch. Right? So very simple. The resolution is. And resolution plays an important role, right, in categorizing your range of reading. See here, your readings are going to vary from 5.1 to 5.5. An equipment with a resolution of 0.1 will help you to categorize your readings into 5 different types, isn't it? And all the readings will either be 5.1, 5.2, 5.3, 5.4 or 5.5. So how many categories of readings you are able to see? 5 categories. This is called, NDC, number of distinct data categories. Number of distinct data categories. Generally, the industry requirement. Again, whenever I say industry requirement, it is called, Automotive Industries Action Groups Guideline. So these guidelines are used across, all automotive industries, even other industries, non-automotive industries also. According to them, any measurement system should have an NDC of 5. Suppose if I replace the gauge with another gauge, having a resolution of instead of 0.1, having a resolution of 0.05. Instead of 0.1, I replacing it with a gauge resolution of 0.05. Now tell me how many readings will become possible now between 5.1 and 5.5?
20.
20?
5. No, it's not 20, sir.
When the resolution is 0.1, how many readings are possible you are seeing? 5 readings.
5 readings.
When the resolution is much better, instead of 0.1, it is 0.05. What will happen to the readings? How many readings?
10.
10. 10 readings will be possible, right? First reading will be, let's say 5.1. Second reading will be 5.15. Third reading will be 5.2. Then this will be 5.25. That means the number of categories of increases. That means, you can understand to a great extent when you have an equipment with a better resolution, right? So whenever you have your NDC is not sufficient, one idea to improve the NDC is go for a equipment with a better resolution, right? And this is the statistical formula. You will gradually understand, the meaning of sigma gauge and sigma parts. Please note, uncertainty is the problem in all our decision. Uncertainty is the function of variation. And how to measure variation? Using certain statistical values. One of the statistical values is standard deviation. So standard deviation is nothing but a measure of uncertainty. Sometimes it is called standard deviation, sometimes it is called variation, sometimes it is called error, sometimes it is called uncertainty. So ultimately, for all the problems in this world, the root cause is standard deviation. The root cause is variation. The root cause is uncertainty. Minimize the uncertainty, certainty will increase. As the certainty increases, all your decisions, can happen as per the findings. Right. Now coming to the repeatability. I want one of you to read out this definition, and so that all of us can try to understand it. Can one of you read it out?
Repeatability is the consistency of a single appraiser to measure the same part multiple times with the same measurement system. It is related to standard deviation of the measured values.
Okay. You are able to understand the meaning? Repeatability is the consistency of a single appraiser to measure the same part multiple times with the same measurement system. Suppose if I ask C.K. Prasad to measure a standard product, a standard part, the standard part is 100 mm. I want Prasad to measure the 100 mm 10 times. He measures perfectly and give me 10 readings and all of them are 100. Now tell me, is he repeatable?
Yes.
Definitely repeatable. All his 10 readings are same. If all the 10 readings are same, variation is 0. When variation is 0, under such situation, if you calculate standard deviation, what will be the value of standard deviation?
0.
0. Standard deviation 0 means, repeatability error is 0. All that required is multiple readings from the same appraiser. He should have collected the data from the same part, using the same measuring equipment, using the same instruction, same condition, environmental condition. But in reality, when I ask Prasad to measure the same part multiple times with the same measuring equipment under the same environmental condition, do you think he will give me the same readings? It's not going to happen. So repeatability error is going to happen. So if you want to estimate the repeatability error committed by Prasad, all that you need to do is just to calculate the standard deviation of his reading. If the standard deviation is 0, repeatability error is 0. If the standard deviation gains value, what is that indicates? It is the error is increasing, isn't it? Error is getting accumulated. So your standard deviation is a measure of the repeatability error. That is the meaning of the last line. It is related to the standard deviation of the measured value. If the standard deviation is more, repeatability error is more. If the standard deviation is less, repeatability will be less. So if you have the knowledge of standard deviation and normal distribution, you can estimate the repeatability error of any measurement system. Looks logical? Correct? Right. And now, let us imagine C.K. Prasad has collected 100 reading, generated 100 reading from the same part. But when he actually works in the project, he may even generate 1,000 reading. He may even generate 10,000 reading. He may even generate 10 lakh reading. Possible. What is going to be the error in all the readings that he is going to collect? Can I simply go behind the Prasad and then check every time? I am not going to work in that way. Only study him once and estimate how much is going to be the total error. That's called a prediction. Isn't it? That's called a prediction. So I will take a sample of reading of an operator, and by understanding the sample data, I try to understand the total error, or I will try to estimate the total error. For that, the knowledge of standard normal distribution will be helpful. Right? And see here, 100 readings of Prasad is available with me, and that is visualized. That follows a normal distribution. Since reading is continuous, the data Prasad collected is a continuous data, maybe a diameter or maybe a perimeter or maybe temperature or something. All of them are continuous data. Generally, all continuous data, it will exhibit this kind of bell shape. We call it normality. And so the center line is the average of the reading produced by the operator. Now, for the same, using the same data, I can calculate the standard deviation. Here is the standard deviation. You all know standard deviation, right? Square root of summation of x minus x bar the whole square divided by n minus 1. And now, the whole lot of readings that are going to come out from a particular operator will definitely fall in this population, in this curve. Definitely the sample will be within the population. Am I right? All the sample data will be inside the curve. Am I correct or not? All the sample data, 100 data will be inside this curve. Am I correct or not?
Correct.
Correct. If the sample is collected properly, if the sampling techniques are proper, the behavior of the sample and the behavior of the population will be almost same. Am I correct or not again?
Yes.
Very good. So, sample characteristics is understood, sigma. Under this curve, how many standard deviations are possible on the right side? This is one standard deviation, right? Let me just draw it for you. Nothing but normal distribution property only, again I am repeating. So up to this thing, one standard deviation. And let me go for one more thing, 2 standard deviation. Let me go for one more thing, 3 standard deviation. When I go up to 3 standard deviation, majority of the curve is covered. Majority of the population can be estimated simply by going up to 3 sigma distance from the center. The remaining is a very small portion. Let us ignore. Similarly, on the left side also, 1 sigma on the left, 2 sigma on the left, 3 sigma on the left, and I am not bothered about the small portion. So totally, how many sigmas are inside the curve?
6.
Very good. Multiply the sigma by 6. What is sigma? Estimate of the error. But how many sigmas are there? 6 sigmas are there. So when you multiply the sigma by 6, that will be the repeatability error. The simple formula. How many of you understand? Calculate sigma, multiply by 6. 6 times sigma will be equal to the repeatability error in your sample data. If the sample is designed properly, same thing can be considered as the estimate of the error in your population data also. Yes, any question here? No question?
No.
So we move on. Now, like how I involved Mr. Prasad, now I am going to involve other operators. Let me involve Ganesh, let me involve Satish, and let me involve everyone. Now, each one of you will give me multiple reading. Each one of you will give me multiple reading. Now, I wanted to understand, I wanted to compare how consistent all of you are as a team, right? So, the first one, the reading given by Prasad. The second one, reading given by Ganesh. And now, look at the Prasad reading. He has, let's say, 100 reading he has. An average of Prasad is here. Average of Ganesh is here. An average of Satish is here. An average of everyone is here. Now look at your team's performance. Do you see some disagreement here?
Yes.
This is some variation. See, when I want to compare myself with yourself, I will compare my average with your average. isn't it? My performance will reflect in my average. I compare my average with your average, and if the average is, do not agree, then the error is called what? Reproducibility error. This is what we call it, inconsistency between the appraiser. Inconsistency within the appraiser is repeatability, and inconsistency between the appraiser is reproducibility. If you want to measure if you want to get an estimate of the reproducibility error, you must have average of all the appraisers. Prasad average, Ganesh average, Satish average, and so on. Let us say 10 appraisers are involved, then there will be 10 averages. With the 10 averages, is it possible for you to calculate a grand average? Average of 10 averages?
Yes.
That is this data line. You have 10 averages. You have 10 averages, that means just 10 numbers. Is it possible for you to calculate standard deviation of the averages?
Yes.
Standard deviation of the averages is given another name called standard error of the mean.
We discussed Tuesday, sir. Last Tuesday we discussed this.
Yeah. Standard deviation of the averages is nothing but standard error of the mean. The standard error of the mean will help you to locate the limits of your confidence interval. We will touch this tomorrow, right? And now, see here, the sigma here. What is the sigma? Nothing but the standard error. The sigma of the averages. Now, how many such sigmas will be possible? 1, 2, 3. Only a small portion of the curve I am not able to understand. If I want to understand the atmosphere of the earth, tell me how many kilometers I should go away from the earth. It is infinite. I cannot go everywhere. I will go only to certain level. Same way, I will go only up to 3 sigma to understand the curve. Right? 3 sigma on the right side, 3 sigma on the left side, and now multiply by 6. What is this error? Reproducibility error. Here, the sigma is reproducibility. The previous one is sigma of repeatability. So, just now, I just taught you how to calculate sigma of repeatability, how to calculate sigma of reproducibility. Multiply by 6, you get an approximate estimate of the error, and then sum of the two. Sigma of repeatability, club the repeatability error, club the reproducibility error. That is the total measurement error. Very simple. But to be more and more accurate, some adjustments have to be done in the formula, and that we will try to understand. Oh, once you have the data available, and in Minitab you can actually conduct a study. Minitab will take care of all your pain of doing the analysis, calculation of standard deviation. Right? We are teaching you only to make you understand. But you can actually always use the Minitab or some template given by RK and then get your results. If you go to Stat, there is an option called Quality Tools. Then there is an option called Gauge Study. Under the Gauge Study, if you click this, create Gauge Study R&R worksheet, a worksheet will get generated. This worksheet will guide you on the data collection process, and a worksheet will look like this. See here, run order, parts. How many parts are selected here? 1, 2, 3, 4, 5. 5 parts are selected. In my opinion, every time you are doing a gauge R&R study, please take at least 10 parts in the preferred range. How many parts? 10 parts, right? But here it is only 5. And then operator. How many operator here used? 3 operator. And this is based on the real-time situation. If there are 3 operators involved, then involve all the 3. If there are so many operators involved, then you can fix according to your choice. You can fix as 3 operator or 5 operator. And now 5 parts, 3 operator, then each part, let us say 5 parts, 3 operator, each part measured 2 times. So totally how many readings you are going to generate? 30 readings. So this kind of format will be generated. Now you conduct the study, you record all your measurement here. Once the measurement are available, feed it in Minitab or find out the standard deviation the way I have explained, multiply by 6, club the standard deviation, total gauge R&R will be with you. So we will again come back to the point.